It's kind of amazing how predictable AI language models seem to be getting, just making them bigger, giving them more data, and their performance just climbs, almost like clockwork. It hints at something fundamental, doesn't it?
It really does. And that's exactly what we're diving into today. We're looking at this key paper, Scaling Laws for Neural Language Models.
Hmm.
It basically uh, maps out how these models improve when you scale up the resources.
Resources meaning what
Yeah.
specifically?
Right. So the model's internal complexity, the number of parameters then, the sheer amount of text they learn from, the data set size, and also the computational horsepower you throw at training them.
Gotcha. And this deep dive, it's really for you, the learner. If you want to grasp where AI language tech is heading, but maybe without wading through all the super technical stuff, this is your shortcut.
Exactly. Our mission here is simple. Unpack the core findings. How does performance scale with these different factors? And the insights, they come from tons of empirical tests, looking at models and data across massive ranges.
Okay, let's get into it then. So, first big finding, it really just boils down to size matters most.
That's the headline, yeah. Performance hinges overwhelmingly on those three things we mentioned. Model size, specifically the non-embedding parameters dataset size in tokens, and the compute used for training.
So, all the talk about clever architectures, different ways of structuring the network, that's less important.
Surprisingly, yes. I mean, within reasonable limits, things like how deep versus how wide you make the network, they have a pretty minimal impact compared to just the overall scale.
Mm.
The paper nails it. Performance depends strongly on scale, weakly on shape.
Okay, that's clear. But then it gets even more interesting, right? Because it's not just that they get better, but how they get better is, well, predictable.
Precisely. They found these really smooth power law relationships. Basically, how the model's error rate, the cross-entropy loss, decreases follows predictable curves as you increase things like training time, model size, data size, or the compute budget.
And these aren't just small trends, are they?
No, not at all. They track these patterns across more than 6 orders of magnitude. Think about that, a million-fold range. There's a chart in the paper that shows it really clearly.
Wow.
Yeah. And importantly, even at the biggest scales they tested, the trend just kept going. Now, they acknowledge performance has to plateau eventually, but they didn't see it starting to break down yet.
So just keep scaling up and up. Is it that simple?
Well, that's where it gets a little more nuanced. You have to consider how model size and data size interact.
Hmm.
That brings in the idea of overfitting.
Ah, right, overfitting. So when the model gets too big for its data boots, essentially.
Kinda, yeah. If you make the model much bigger, but don't feed it enough new data, or the other way around, it starts down the air. Well, memorizing the training examples instead of learning the underlying patterns, performance on new stuff suffers.
And is that overfitting predictable too?
It seems to be, yes. They talk about the universality of overfitting and even give an approximate formula. It looks something like n to the power of 0.74 divided by d model size versus data size.
Okay, what does that mean in practice?
It means, roughly, if you make your model, say, 8 times bigger, you don't need 8 times more data. You only need about 5 times more data to kind of keep that balance and avoid a big hit from overfitting. It gives you a real sense of the data appetite of these large models.
That's actually really helpful. So it's not a strict one-to-one scaling needed for data.
Exactly. And, speaking of predictability, the training process itself seems to follow these power laws too. How quickly the model learns seems pretty consistent, surprisingly independent of the final size of the model.
So you can get a sense of how well it's going to do quite early on.
That's the idea. Looking at the initial training progress, you can make a reasonable prediction about its final performance, its final error rate, even if you plan to train it for much, much longer.
Okay. Now, what about generalization? If a model does well on its training text, does that mean it'll be good on, say, different types of text it hasn't seen?
Generally, yes. That's another key finding. Models with lower error on their training set also tend to perform better on different text distributions. There's usually a kind of fixed performance gap, an offset in the loss, but the improvements carry over. It shows they are learning general language abilities.
That's crucial for actually using these things, right? They're not just memorizing one data set.
Definitely. And this leads to something quite counterintuitive.
Yeah.
Bigger models are often more sample efficient,
Sample efficient meaning.
meaning they reach the same level of performance as a smaller model, but they do it after seeing fewer training examples, fewer tokens. They learn faster, in a sense.
Wait, they need less data to get to the same point?
In terms of tokens processed during training to reach a specific performance level, yes. Figures in the paper show this quite dramatically.
Mhm.
Larger models hit target error rates way sooner in terms of data seen.
That really does go against intuition. You'd think bigger means hungrier for data.
You would, but the evidence points this way. And it ties into another really practical point about training strategy. Maybe training models all the way to convergence until they absolutely stop improving isn't the best use of compute.
Don't train them fully. Why not?
Well, the paper suggests that for a fixed amount of computing power, you actually get better final performance by training a very large model and stopping it well before it's fully converged, rather than training a smaller model to its absolute limit.
Huh. So go big, but maybe don't train it quite as long.
Exactly. Training for maximum compute efficiency seems to be much more sample efficient. And the amount of data you need for this efficient approach grows surprisingly slowly compared to the compute increase, something like data size scales with compute to the power of only 0.27.
Okay, that's a really interesting strategic insight. Now, these power laws, can we simplify them a bit? What are they actually telling us?
Sure. Think of them as mathematical descriptions of diminishing returns. The loss, L, which is our error measure, goes down as model size N, dataset size D, or compute, CMMN, goes up, but it doesn't go down linearly.
Right.
It goes down according to N raised to some small negative power like madical 0.076 or D to the nadical 0.095 or C minus to the negative 0.050. These small exponents mean that doubling the size or data or compute gives you an improvement, but the rate of improvement slows down as the numbers get bigger.
So each doubling gives you less of a percentage improvement than the previous doubling.
Precisely. And the exact starting points for these curves, the constants involved, depend on things like how you tokenize the text, the vocabulary size. So they aren't quite universal physical constants, but the exponents, the rates of scaling, seem pretty consistent.
Got it. That explains the diminishing returns aspect. What about this critical batch size they mentioned?
Yeah, bcrit. That's about finding the sweet spot during training. It's the number of examples you process in each step that gives the best trade-off between training speed and compute efficiency.
And is it a fixed number?
That's the interesting part. The optimal batch size actually changes as the model gets better, as the loss goes down. It follows its own power law. So you ideally want to adjust your batch size during training to stay near this critical value for maximum efficiency.
Okay, another dynamic factor to consider. And you mentioned the combined effect of model and data size earlier. Is there an equation for that?
Yep, they propose an equation, LNNHAA, that captures how loss depends on both N and D together.
Well,
It's pretty good at predicting performance, and it formalizes how the balance between them dictates overfitting. They even use it to estimate a rough guideline. You probably want your dataset size D to be bigger than about 5 by 103 times N to the power of 0.74 to stay clear of significant overfitting.
that's a handy rule of thumb. So, putting it all together, if you get more compute budget, where should you put it? Bigger models, more data, longer training.
The strong suggestion from the data is, put most of it into making the model bigger. As compute Cmin increases, the optimal model size, N, grows quite fast, like Cn to the power 0.73. The optimal batch size, B, grows too, but slower, like Cmin 0.24. And the number of training steps, S, grows really slowly, Cmin 0.03.
So the overwhelming message is scale up the model size, first and foremost.
That seems to be the most compute-efficient path to better performance, based on their findings.
That's
And this is a fascinating twist. When they projected these trends out to really enormous scales, they found a potential contradiction.
Oh, what kind of contradiction?
Well, the amount of data that seems optimal for compute-efficient training, remember, D scales like Cmin 0.27, appears to grow slower than the amount of data needed to avoid overfitting based on the LD scaling law alone.
So at some massive scale, you might not have enough data to train the optimally sized model efficiently without overfitting.
That's the puzzle, yeah. They conjectured that the point where these different scaling trends intersect might represent something fundamental. Maybe it's the practical limit of these transformer models, or maybe it's even related to the inherent complexity, the entropy of natural language itself.
Wow.
They throw out some huge numbers like 104 petaflop days of compute, maybe 10,012 parameters, and 10 Velocity tokens, but stress, these are very rough estimates. Still, it's this tantalizing idea that there could be a ceiling defined by the scaling laws themselves.
A potential endgame for scaling, dictated by the maths. That's pretty mind-bending. And just to reinforce the earlier point, they showed visually that shape doesn't matter as much.
Exactly. Figure 5 is the one to look at there. It shows different architectures, tall and thin, short and wide, all landing near the same performance line, as long as the total number of non-embedding parameters is the same. Really drives home the dominance of scale over specific design choices within the transformer family.
And the sample efficiency thing, that's shown visually too.
Yep. Figures 2 and 19 are great for that. You can clearly see the curves for larger models dropping down to lower error levels much faster after processing fewer tokens than the smaller models.
Okay, so let's try and synthesize this. What are the absolute must-remember takeaways?
Let's say 1, scale is king. Model size, data size, compute power are the main drivers. 2, performance improvements follow predictable power laws, which is huge.
Yeah.
3, the interplay between model size and data size is crucial for overfitting, but there's a formulaic relationship. And 4, maybe the most surprising. Bigger models are more sample efficient, and optimal training might mean using very large models but stopping them before full convergence.
And that leads to their final provocative thought.
Right. The idea that big models may be more important than big data. It really flips the script on traditional machine learning wisdom sometimes. It makes you wonder about the path forward. Is it just about building ever larger structures?
Definitely food for thought. And for you, the learner, if you want the nitty-gritty details, the equations, the specific charts, check out the paper itself, 2001.08361v1.pdf. But hopefully this conversation gives you the core concepts and the why it matters behind these scaling laws.
And it leaves us and you with a big question, doesn't it? What future breakthroughs might these predictable scaling patterns enable? Could we forecast the next big leap in AI capability? Or how will this focus on scale shape AI research priorities?
Lots to think about. Thanks for joining us for this deep dive.